Section 3.2, the fundamental theorem of calculus and anti-differentiation. Our objectives are 1. Make calculations using the antiderivative. 2. Understand and use the fundamental theorem of calculus. And 3. Understand and use the second fundamental theorem of calculus. The fundamental theorem of calculus is as follows. The integral from a to b of a derivative function, big F prime of x dx, is the difference between the function evaluated at the upper limit of integration and the function evaluated at the lower limit of integration. Notice that this is the derivative of this function. Suppose you want to find f of x if f prime of x, the derivative of f of x, is 3x squared. You know that if f of x is x cubed, then the derivative f prime of x would be 3x squared. But that's also true for f of x equals x cubed plus 7, or x cubed minus 15, or f cubed plus pi, or x cubed minus e, etc. It's true for any function x cubed plus or minus some constant. So although a function has one unique derivative, a derivative has many functions. Recall that the constant is a vertical shift of the function. So the only difference between these two functions is where they are on the graph. So if this was 3, this one would be here at negative 15. Well, let's just say this is negative 15. This one would be here. So the constant is a vertical shift. It's just moving it up and down. So knowing the derivative tells you the shape of the function, but it doesn't tell you the location. Let's talk about antiderivatives. An antiderivative of a function f of x is any function capital F of x where the derivative of the capital F function is the little f function. The antiderivative of a function f of x is a family of functions. So we write it capital F of x plus c, where c is any constant. It's not just a constant, any constant. So back in our examples here, of course I could not make an exhaustive list of all the functions that have a derivative f prime of x that is 3x squared, because there are an infinite number of them because of all the constants that I could add or subtract from them. So this is part of the family of functions that have this as a derivative. We could also write x cubed plus some constant, any constant. So using integral notation in our example above, the integral of 3x squared dx is x cubed plus c. This is called an indefinite integral because there are no limits of integration. Let's take a look at some more notation for the antiderivative. The integral of f of x dx, where f of x is the integrand, the function to be integrated. So the verbs, we say we integrate, or we anti-differentiate, or we find the indefinite integral of a function. The process is called anti-differentiation, or it's called integration, either one of those. Find an antiderivative of 4x cubed. The solution, I can pick any function with a derivative of 4x cubed. So I'll choose, just for fun, capital F of x is x to the fourth plus root 2, because this is a constant. Find the antiderivative of 4x cubed. The solution is the integral of 4x cubed dx is x to the fourth plus c. Find the integral of e to the x dx. Our solution is e to the x dx is e to the x plus c. The fundamental theorem of calculus restated. We said on the previous page the integral from a to b of capital F prime of x dx is f evaluated at b, the upper limit of integration, minus f evaluated at a, the lower limit of integration. The definite integral of a derivative from a to b gives the net change in the original function. Now, to get from here to here, all we've done is add a capital F of a to both sides. So, capital F of b equals capital F of a plus the integral from a to b of f prime of x dx. The amount we end up with is the amount we start with plus the net change in the function. Let's do an example. Suppose capital F of t has the derivative capital F prime of t, whose graph is shown below. So the graph below is the derivative. And we know that capital F of 0 is 3. Find values for capital F of 3 and capital F of 5. So we know that we're looking for the area. We know that capital F of 3 would be capital F of 0 plus the integral from 0 to 3 of capital F prime of x dx. And we have this value here. So we know we've got a 3 here. And what we want to add is this. And we know that this is the area under the curve and above the x-axis from 0 to 3. So we know, and you want to watch this graph again, I've got the units, every 2 squares is 1 unit. So here we go from 0 to 3. Now it looks to me like this is 1. This is 1, and this is a half. But let's go ahead and calculate it. So I can see that this is a trapezoid. So since the graph is all above the x-axis from x equals 0 to x equals 3, I know that I'm going to have all positive area. So the area would be 1/2 little base plus big base times the height. So here's my little base, 1, 2. You can also see 3 minus 1 would be 2, plus the big base of this trapezoid here is 3 minus 0, so 3 times the height, and the height here is 1. So 5/2, which would be 2 1/2. So 1, 2 1/2. just as we predicted. So capital F of 3 is 5.5. That it is f of 0, which was given to us as 3, plus the area from 0 to 3, which we just calculated. So let's go ahead and find capital F of 5. So capital F of 5, I'm going to leave a little more space here so I can write the integral. Capital F of 5 would be f of 3 plus the integral from 3 to 5 of capital F prime of x dx. And we already know capital F of 3 because we just calculated it, plus the area from 3 to 5. So here's 5. So the area we're talking about would be this area here. Now you can see that we are above the x-axis from x equals 3 to x equals 3.5. So this is going to be positive, and we are below the x-axis from x equals 3.5 to x equals 5. So we're going to subtract this part. And if we're just looking at this, we can see what we expect. These two triangles are the same area, so if we add this and subtract this little piece, that would be 0, and then we're going to end up with a negative 1. But let's go ahead and calculate it. So the integral from 3 to 5 of f prime of x dx is the area from x equals 3 to x equals 5. And that would be one-half base times height minus the area under the x-axis, which would be 1/2 base times height. Let's see, if I look at this as a triangle, that would be 1/2 base times height plus this square, or I can calculate it as a trapezoid, and I'm going to do that. Little base plus big base times the height. So that would be 1/2 the base of the triangle. This is 3.5 right here, so that's 1/2. The height here is 1 times 1 minus 1/2 little base 1 plus big base. This is 5 minus 3.5, so 1.5. Let's just use 3/2. Times the height. The height here, 7 minus 6, so 1. So the area is 1/4 minus 1/2 times 1, 2, 5/2 equals 1/4 minus 5/4 equals -1, as predicted. Because we looked and we saw this is a -1 square, and this is a -1/4 triangle, and this is a +1/4 triangle. And we're done. Recall, you know a lot about the graphs of functions and their derivatives from the end of Chapter 2. Where the graph of the derivative is positive, the original function is increasing. Where the graph of the derivative is negative, the original function is decreasing. Where the graph of the derivative crosses the x-axis, the slope of the original function is 0. So these x values would be where local extremes occur. The fundamental theorem of calculus, part 2. The area is the integral from 0 to x of f of t dt. Then the derivative of that function is the derivative of the integral from a to x of f of t dt. The derivative of the integral is the function at in terms of x. That is, the derivative of the accumulation function. The accumulation function is the original function. So the graph of f of x is the graph of the derivative of the accumulation function. So let's let the accumulation function be the integral from 0 to x of f of t dt with f of x shown below. So what we're saying is, if the accumulation function is the integral of this function, then this function is the derivative of the accumulation function. So this is what we're looking at. So we're looking at the graph of a derivative, and we want to find out information about the initial function, the accumulation function. So where does it have a local max? I can see for each one of these zeros, each one of these zeros is where the slope is 0. So in the original function, these would be our flat spots. So let's make a little chart and keep track of these zeros. So this is, here in this graph, each square is 1 unit. So this is 1, 2, 3, 4, 5. That's 0. This is -1. So I want to keep track of all of these zeros. So -1, 1, 3, and 5. And here, the derivative is 0. And now I want to see the sign of the derivative in all of these intervals. So I can see that to the left of -1, the derivative is positive. Between -1 and 1, the derivative is negative. Between 1 and 3, the derivative is positive. Between 3 and 5, the derivative is negative. And to the right of 5, the derivative is positive. So what does this tell me about the function again? So where all the zeros are, I've got a flat spot. So this isn't a negative sign. This is a flat spot, just like what I would draw a flat spot on the original function. So positive means the function is increasing. If the derivative is negative, that means we're decreasing. So I'm just going to move this flat spot down here so it's connecting. Here, the derivative is positive, so the original function is increasing. Here, it's negative, so the function is decreasing. And again, I'm going to move my flat spot down. And here we're increasing again. Now I drew it this way on purpose because this is actually kind of what our graph looks like. And when I look at this, I can then see at what x value does a of x, the accumulation function, have a local max. The original function looks like it has local max at x equals -1 and 3. At what x values does the accumulation function, capital A of x, have a local min? So looking here, I can see we've got a min at x equals 1, and again at x equals 5. Let's talk some more about graphing that you already know. The graph of a function is concave down where the second derivative is negative, where the second derivative is less than 0. The graph of a function is concave up where the second derivative is positive, so f double prime of x is greater than 0. Let's do an example. Recall some key characteristics of the derivative that give us information about the original function. If the first derivative is positive and increasing, increasing tells us that the second derivative is positive. So if the first derivative is positive, that tells us the function is increasing. If the first derivative is increasing, that tells us the second derivative is positive. That tells us the function itself is concave up. If the derivative is positive and decreasing, if it's decreasing, that tells us the second derivative is negative. So the function must be increasing and concave down. If the function derivative is negative and increasing, so remember this is, if it's increasing, the slope is positive, so the second derivative would be positive. So if the derivative is negative and increasing, that is the second derivative is positive, then the function itself must be decreasing and concave up. If the derivative is negative and decreasing, so decreasing meaning it's got a negative slope, that tells us the second derivative must be negative. So if the derivative is negative and decreasing, then the function must be decreasing and concave down. Example 6. Given a derivative function, quantity x minus 1 times quantity x plus 4 times quantity x minus 5, describe the function at the following x's, -5, -3, 0, and 2. In particular, is the function itself increasing, decreasing, concave up, and or concave down at each of these x values? So, if we're going to calculate the second derivative, we're going to need to multiply this out. So, the first derivative I'm going to first multiply these two together. So x squared plus 3x minus 4. And then I'm going to multiply that by x minus 5. So I'm just going to flip these around. So I'm going to multiply each of these terms by x. And now multiply each of these terms by -5. And here we go. So we have the derivative. Now we can find the second derivative. And there we go. So if we want to describe what's going on with the function at these points, if I evaluate the derivative at each of these points, if I get a positive number, then I know I'm increasing. If I get a negative number, then I know I'm decreasing. If I evaluate the second derivative at each of these, I can tell whether I'm concave up or concave down. So I'm not being lazy, I'm going to be efficient. I'm going to set up a little chart, and we're going to put these into the tables. So I've got in the first y equals, I've got the derivative function we've been given, x minus 1 times x plus 4 times x minus 5. And then in the second spot, I've got the second derivative, 3x squared minus 4x minus 19. And I'm going to go to the tables and evaluate each of these. And remember, I'm looking for increasing, decreasing, concave up, or concave down. So on my chart at x equals -5, -3, 0, and 2, I'm going to actually only record the sign of our derivative function and our second derivative function, and then we will describe what is going on with the function at those points. So if I go second table, so here at -5, the first derivative is negative, the second derivative is positive. At x equals -3, the first derivative is positive and the second derivative is positive. At x equals 0, the first derivative is positive, the second derivative is negative. And at x equals 2, the first derivative is negative and the second one is also negative. So if the derivative is negative, the function is decreasing. If the second derivative is positive, it is concave up. If the first derivative is positive, the function itself is decreasing. If the second derivative is positive, then the original function must be concave up. If the first derivative is positive, the function must be increasing. Whoa, I wrote that one wrong there. First derivative positive, we're increasing. Second derivative positive, we're concave up. First derivative positive, we're increasing. Second derivative negative, we're concave down. First derivative negative, we're decreasing. Second derivative negative, we're concave down. We've got one more little piece of the puzzle to get through for this section. The second fundamental theorem of calculus. If f is continuous on an open interval I containing a specific xa, then for every x in the interval, the derivative of the integral from a to x of f of t dt is the function evaluated at x. The derivative of the integral, notice this is the same function. By that limit of integration, we have just changed the variable. Restated, if a function is the integral, then the derivative of that function is the function inside the integral. So the derivative of the integral is the function. The derivative of the integral is the same function. We've got to change a variable here. We've gone to the x from the t, for example. That implies that if the function is the integral, then the derivative is the integrand. If the function is the integral, then the derivative of that function is the integrand. But again, we've changed the variable with the limit of integration. So I loved these when I learned how to do this. If the function is the integral from 3 to x of x to the fifth, find the derivative of x. Well, the derivative of the integral, we're just going to change the variable. So f prime of x is x to the fifth, and f prime of 3 would be 3 to the fifth. So I believe that is 243. All right. That's the end of section 3.2.